Good evening, ladies and gentlemen. I am Engineer Pragit Vijay Sri Lanka, Secretary of Sri Lanka Section of American Society of Civil Engineers in USA. I welcome all of you to this webinar session about design and construction technologies in high-skewed bridges, case study with the greatest skewed bridge in Central Expressway, Section 2 in Sri Lanka. I will invite Engineer Kamala Gunawardana from Civil Engineering Sectional Committee in Institution of Engineers Sri Lanka to give some introduction about today our resource person. Engineer Kamala, is over to you now.
Thank you, Engineer Pragit. Am I audible?
Yes, Kamala.
Thank you. Good evening to all of you. As you know, I'm Kamala Gunawardana, Council Member from the IESL and the Chairperson of the Civil Engineering Sectional Committee of this Knowledge Sharing Subcommittee. So, as a highway consultant, actually, I'm really happy to join this webinar, and I'm honored to give this instigating speech today. Also, I am happy to say that Civil Engineering Sectional Committee, we have contributed a lot. We have shared more and more knowledge among our members of the IESL as well as other professional bodies like IC, UK, and now USA chapter as well. So from these programs, we could develop our instincts, insights, and also to develop our professionalism while achieving a better living standard. So about the today's webinar, this is about the design and construction technologies in high-skewed bridges, case study with greatest bridge in CP2, that is from Meerigama to Kurunegala. So the CP2 project was remarkably cherished by almost all the citizens in the country during past few months. Main specialties for the project was fully accomplished by these local resources, including financing, design review, construction supervision, project management, and so on. Right now, let me introduce the resource person for this webinar today. This Engineer Sumana Singha. Now he is not a unknown person or someone. Now he is very much with us with several webinars. So he's a consulting structural bridge engineer he was the consulting structural bridge engineer for Central Expressway Section 2. He's a product from University of Moratuwa, graduated in 2004. He obtained his master's from Griffith University, Brisbane, Australia. He's an OSCE scholar and received academic excellence for his master's studies in Griffith, Australia. So these are some of his the small quantity of achievements. Further, he is a member of the Institution of Engineers UK, Institution of Engineers Sri Lanka, and Society of Structural Engineers Sri Lanka. He is serving as a professional review panelist at the IESL. Engineer Cell has more than about 18 years of experience in structural design, and he has worked in infrastructure projects funded by ADB, World Bank, and JICA. Actually, his expertise is directly associated with design of structures in expressways and highways, including major structures such as viaducts, bridges, overpasses and underpasses, superstructures with pre-stressed concrete girders, including continuous girders, box girders, steel concrete composite structures, steel truss bridges, etc., etc. Yes, we are starting the event right now. And without further ado, I hand over to Engineer Yasela Sumanasinghe to proceed it. Yeah. Please enjoy this evening. Thank you, everyone. Thanks a lot.
Thank you very much, Engineer Mrs. Kamala Gunawardana, for your kind invitation. And thank you very much, Engineer Pragit Vijay for your introduction for this lecture as well. And I have to thank Civil Engineer Sectional Committee of Civil Engineer uh, Institution of Civil Institution Engineer Sri Lanka, as well as the Sri Lankan chapter of the American Civil Engineer Society, giving me this opportunity to present this part of our construction experience in Central Expressway Section 2, Girigama to Kurunegala, and discuss some design and construction aspect of this valuable project. So I will start my screen sharing. So today I'm going to talk about the Skewed bridge designs and how this Skewed affect for the design of structures, Skewed bridges, Pothuhara intersection of Central Expressway. Now you see in this photo the Pothuhara interchange, which do have two ramps, and these are about nearly 55 degrees Skewed bridges, and one is ramp A and other one is ramp D. So this is a system interchange. What do you mean by system interchange is this is a interchange where one expressway connect to the another expressway, but there are no exit or entrance point, direct exit or entrance point for the normal traffic. Just only changing from one expressway to another expressway. So as we all know, as Sri Lankans, the Mirigama to Kurunegala Section 2 Central Expressway was successfully completed and it's open for traffic presently as well. And the Section 3 from Pothuhara to Galagedera, from this interchange point to Galagedera, it's under construction, directly managed by the Road Development Authority and the local contractors. So that part is ongoing. And so today I'm going to discuss about the Skewed bridge explicitly, but the case study in the Pothuhara interchange in the Central Expressway project. So I have divided this lecture into few categories, few subheadings. So first I will discuss about the terminologies related to Skewed bridge, and I will discuss about the effects of the skew due to the skew, how it's affect to the structure and how it's affect to the structure design, and why we need to worry about this skew. So then we will go to the design solutions. Maybe we detail with the detailing the bridges for skew, how to do that one. Then I will go into little bit of in-depth design aspects for the Skewed bridge designs, which include the deck analysis. Then I will move into the construction and design technologies we used in Pothuhara to overcome the effects of into skew. Then I will little talk about how to what are the effects on substructure due to skew and how it will affect, and how we compensate these skew effects. So in the right hand side, you will see another photo of the Pothuhara interchange. This is we call ramp D. This was taken during the almost complete end of the completion, but still constructions are going on. So this is ramp D. So what do you mean by a skew angle in the bridge? So it is defined as an angle between the center lines of the support. So if you see, check point options. Yeah. So I hope you can see my laser point. So I will be able to show you what I mean by these wordings. So angle between skew angle is angle between the center line of the supports. So this is the supports of the bridge skew bridge, and line normal to the roadway center line. So if we, this is the now this picture is from the underneath of the bridge, not from the top. We come into the next slide, but this is underneath of this bridge. So this is the center line of the bridge, and this is the uh, line joined by the um, supports of the bridge. And when you draw a line perpendicular to the longitudinal axis of the bridge, and angle formed by these two lines will create the skew angle. So this picture is much clearer what I'm going to explain here. So now this is the supported edges, and these two are the supported edges, and these are the free edges of the bridge, and the angle you we take as the perpendicular to the free edge and the supported edge we call the skew angle. Now there are two main angles two angles formed by the skew of the bridge. Now if you see, there is an acute angle here between the free edge of the supported free edge and the support edge. This acute angle we call acute corner, and there is another obtuse angle here. We call that one obtuse corner. So based on the angle value less than 90 or greater than 90, we define this one acute or obtuse corner. This is very important to discuss about the skew effects of the skew in a bridge. So now we have a definition in RDA bridge design manual in Sri Lanka. If you see, there is no any other design specification. Local design specification for the design other than the bridge design manual developed by the Road Development Authority in 1997. Since there is no any other code of guideline other than the code of practice, maybe BS 5400 or Eurocode, we rely on the bridge design manual for the local conditions. So what it say about the skew? So it's first define the skew as similar to we discussed earlier slide. The skew is defined as the skew angle is defined as the inclination of the abutment the perpendicular to its free edge, similar to what we discuss here. It's define the skew angle. Then it's say an important aspect here. When the skew angle is less than 20, it says you don't bother about the skew. Just go like it's a right angle bridge. The detailing of the bridge or the detailing of the SAB can be accommodated as the normal bridge, and you may use a normal type of girders irrespective of the skewness if it is less than 20 degrees. But if it is greater than 20, you have to check whether the skew effects to these bridge design, beam girder designs, deck designs, etc., etc. So now RD is giving this 20 degrees limitation. So if you go to the other code of practices or other design guidelines given by the several other highway agencies, let's say UK or Australia, this value is somewhat some little different. It varies some from 20 to 30. Some American standards say it's 30, and maybe Australia is sticking to the 20. So this may be 20 to 30. So in Sri Lanka, we stick to the 20 degrees margin. So now let's see what is happening when there is a skewness in the bridge deck. So if you know, this is the normal bridge deck, which is supported perpendicular to the longitudinal center line of the bridge. And this is a very normal bridge, and we now we call it, we can call it as a supported bridge. And when you have the load here distributed to these two ends, and the load path is in between the two supports. So its load is divided to support like this, as denoted by the arrows. So what happened when there is a skew? When there is a skew, the load path doesn't act as a similar to the right angle bridge. It uh, it goes from the obtuse corner to other obtuse corner, and as a result, there is so many effects of the in the bridge deck. Now this is a more elaborative schematic drawing. What is happening here? Now if you see, now this is the support here. So and this is the support here. Now this support is spanning not between the now load transfer is not between these two supports. It transfer between the one support and the free edge of the deck. So if the skewness is high, this effect is very high. As a result, there will be so many effects which we are going to discuss. Now this is another illustrative of the what we are going to happen due to the skewness. Now there will be a uplift in the acute corner, and there will be a high shear forces at the obtuse corner, and also reaction forces at the obtuse corner. Now this is happen due to the load path what we have discussed here. So all the loads transferring to this obtuse corners. So that as a result, there will be a high reaction in the obtuse corner, and load transferring to acute corner is less, so that shear forces are less, and perhaps there may be a uplift and lesser reaction forces at the acute corner. So these are the load paths clearly defined what is happening. So if you have a skew deck, we are with less torsional distribution system, you can see that will happen in the deck. So what will happen if we not properly address these issues in a skew slab? There will be cracks. So this is I took this from a picture from something somewhere else, not in the Central Expressway, to illustrate what kind of cracks will develop in the deck if we not address these skew issues in correct manner. So there will be corner cracks similar to this one, and this may happen owing to the loads, as well as these cracks may appear during the construction stage as well, because there may be diagonal cracks. Main contributor, the research papers say most of the crack appeared in the skew bridge decks were due to shrinkage and concrete, the high temperature issues in the concrete mixers. So we may now sometimes design engineers may tend to heavily reinforce these skew obtuse corners and acute corners to get rid of these cracks. But again, we have to keep in mind that heavy reinforcements also restrain the structure from shrinking. So it's act as a restraint. So there will be cracks owing to that one as well. So we have to little careful when we dealing with the skew effects. So as I described, the problem associated with the skew are about it's basically there's a modified load path, and there will be high shear forces in the obtuse corners, and there will be reduced shear forces in the acute corner, and there may be a possibility of uplifting. And now if you see, girder moments reduce, but torsion and negative moments increase. Now what is happening here? Now I go to this page again. Now if the load path is like this, the girder moments, longitudinal moments are very high. But when there's a skew, there is a lateral distribution of loads. So as a result, the longitudinal moments will get reduced in the girder, but it will increase the torsional effects, torsional effects uh, forces in the girder. So that's what this number 4 is about. And there may be possibility negative moments at the corners as well. So now this skewness, due to this skewness, there are so many, as we described, that uplift in the acute corner, and there are high shear forces in the obtuse corner, and there are some lateral torsional effects on the deck, so that there may be large horizontal displacement in the deck. So what that mean? That means it's affect to the bearings and the expansion. So with the time, you will see the bearing under the girders may be displaced or damaged, and even the expansion joints are get damaged, or we have to replace within a shorter period. Generally, the time period, general lifespan of a bearing pad may be about 25 to 30 years, or expansion joint about is again 25 to 30 years. But if we not address the skewness of the bridge correctly, we have to replace this one, or uh, revisit these places time to time frequently. So now to do that one, we can restrain these movements. So how that we can do is, we can go for the integral bridges, we can do doweling and all those stuff, and it may cause, if we not design this one, we may get a cracks in the deck. So we have to either restrain the movements, and we have to heavily reinforce the deck, or otherwise we allow the bridge to breathe, I mean move. So we call it, we allow the superstructure to breathe, and we allow this bearing and expansion joint such a way that it accommodate all these movements. So these are the two choices we have to make when design the bridge articulation. So now all these effects depend on the how much this deck is torsional high stiffness. Now what is this torsional stiffness is mean? Now if you take a deck, if you load the deck in a sideways, how much it will transfer these loads to other end laterally. So if there's a high torsional effect, it will correct greater transfer. But if there's a low stiffness in the bridge deck, there is a low transfer of forces lateral. So normally, generally, if the box girder types, cellular decks, even the high depth solid step has a solid slabs, do have a high torsional stiffness, so that I described earlier will be high. But if you consider the low torsional stiffness decks, such as beam slab bridge decks, the torsional stiffness is less because all the lateral load can slab thickness compared to the high depth of the composite structure. The lateral forces, uh, lateral sharing is less, so that skew effects are less. But disadvantagely, you will get higher bending moments or ultimately higher pre-stress for your girders. That's the decisions we have to make, whether when you are choosing whether we go for low stiffness in torsional or high stiffness in the torsion. So higher pre-stress mean higher bending moments mean we give to give more pre-stress, or otherwise we have to deep girders, and then maybe then other issues come into picture, that no less clear height and low tolerances, those stuff. So it's a decision you have to make as a designer when you choose your structural superstructure system. So now this is another picture what we have. This is about our Potuhari interchange. Now this is about RAM T. So you see the skewness of the bridge, and this is the girders we have used, and so this is a beam and deck slab type of bridge deck, so that we have minimized our skew effects. However, we have to design the bridge decks for their larger moments and with the high pre-stress. Now I'm going to my third part of the lecture, where how do we detail the skew bridges. Now, if you see this acute angle, we can produce the reinforcement like this, but what happened here, there is no any bonding length for this corner reinforcement, so that these are not effective. So that although we produce this reinforcement here, there's no any bonding length for this one, so that it is effectless, and there may be cracks in the corner. So it's like we have produced a section with unreinforcement, so that there will be spalling of concrete and chipping of concrete. So we have to do the correct detailing when we do the detailing, reinforcement detailing for the skew bridge. And so what we can do for this this issue. So what we can do is, we instead of going like this, we put a break back. We call break back. So the deck can be have this kind of this part, so that there is no corners, that there are sufficient space as to put the reinforcement, and this we reduce the acute corner effects by putting this kind of geometry for our decks. So this is the bridge deck, and this is the abutment structure. So we modify our bridge deck as like this shape, so that we have sufficient space in the acute corners and obtuse corners to do the reinforcement detail. So that is another way of get rid of this problem. Another one is, we put more reinforcement, allow such a way we fan out the reinforcement like this, and we provide sufficient reinforcement to cater the radially to cater those expected cracks. So if we take let's say 3 meter bar, 3 meter long bar, and we put like this to compensate all the cracks. So this is another way of detail. Then we come to the how do we place the bridge girders in the abutment structure. So either we can keep like this, the straight square end of the beams like this, or we modify these girders like this on the plan uh, in the abutment. So both way are allowed. It's depend on the what you are restrained at the site. So generally, if you see uh, casting of this kind of shape is difficult. This is very straightforward, but it's depend how do you want to do this one. Then again, in the slab, we can do the reinforcement in different ways. So all these three types are allowed. There is no any hard and fast rule. You should go for type 1, type 2, or type 3. You can do it, but you have to design. That's the only requirement. So one way is you put the main bars in the parallel to the free surface, free edge, and distribution parallel to the supports. So other ways you put the main reinforcement perpendicular to the supports and parallel to the distribution parallel to the support. In the type 3 you put main reinforcement parallel to the free edge and distribution steel perpendicular to the main steel. So these are the three types. Literature shows that type 3 has a better performance. Let's say not the better performance, I would say higher bending resistance, but it doesn't matter. Type 1, type 2, type 3 all are allowed, but you have to do the design. So to do that one, there is a theory called wood and armor moments. For we can use this one because in a skew slab there is a direct bending moment, and as I said, due to the high skew there is a torsional moments also. So what wood and armor moments will do is it combines all this stuff and give you the bending moment for the particular direction you want. In softwares, we use this kind of interpretation for to the direction definitions, and we need to get the correct bending moment for the reinforcement direction we are putting. So you can't get this direction of reinforcement bending moment, and you can't put the reinforcement in this direction. So what you have to do is you have to correctly identify the bending moment for the respective direction, and you have to take account the plane bending moment and the torsional bending moment both together and put the reinforcement. If you do so, there will be no any issue with your deck. Now, when it comes to the analysis of the bridge deck, generally we do use grillage measures for analysis of the bridge decks. So if you see, this is the bridge deck, and this is a concrete slab, and there will be girders like this. And so to simulate this one, we use this girder. These are girders, and these transverse elements are denoted in the slabs. So one may can ask why you can't you just model this slab and beam together together at once. The problem is in bridge design you do have a composite action. So first you cast the naked girder, then after launching the girder, then you put the slab on top of that one, and after getting this deck concreting get stiffened, this act as a composite girder. So you have to model such a way that we all these effects can be taken into account at different stages. So it needs some kind of a special arrangement to analyze these decks. So we go for the technique called grillage mesh. So even the grillage mesh, we can do it in a three types. So first you, now if your girder is like this one, you put your grillage deck in this way, and your slab is mesh as perpendicular to your longitudinal girder. And other way is doing so is, you define your girders similar to what you arrange at the side, and then you put your slab transverse element parallel to the supporting edge. So both ways are okay. It doesn't matter. You can do it. So literature shows that for ridge decks less than 30 degrees, so you can go for the this kind of simple grillage mesh. But if it is greater than 30, you have to model your transverse element perpendicular to your main girders. So when it comes to meshing the grillage, the transverse members simulating the slab. So that how many number of transverse element we have to make. It's generally 2 times d2 or 3 times d of the slab. So generally the spacing of the transverse members should be sufficient for represent the load distribution along the longitudinal members. So this is a general way of doing this one. And you see a nice picture of again the ramp A in Potuhera interchange, and it was during this picture was taken just before the opening during the construction. So with that, I will move into with that I complete the tedious part of this design subject, and I'll into more general construction topic in Potuhera system interchange. So here you will see now this is the system interchange we do have, and this is the ramp. We call it ramp A, and this is the other ramp bridge. This is we call ramp T. So this is another way. So towards this way it's Colombo. Towards that long mountain side it's Kurunagala. So you will see this bridge when you pass in this Potuhera. You will feel how skew it is, and please watch that, and keep looking on the details for this bridge when you're traveling along this road. And this part is still under construction, and these parts have been constructed. So what will happen here is, now this is Kurunagala in this picture. This is Kurunagala. This is Colombo. So so when vehicle comes from Colombo, you can go like this and go to Galagedera like here. If you come in from the Colombo, you take this ramp and you can go to Galagedera. You can decide in this way. And if you are coming from Galagedera, again you can come in this path and join to the Kurunagala from this ramp. So these are the two ramps what I'm talking about. This is another picture from the Kurunagala side. So, this was taken from the Colombo side. This is another picture from Kurunagala side. So this is ramp A, this is ramp T. So this is the part I'm going to take my case study. This is another nice picture of this one. So this is ramp A, and this is ramp T. So this is ramp A. So this picture is about ramp A, and this picture is about RAM D, what we can see in this part. So I have already done a seminar or presentation on Central Expressway project earlier uh, with the invitation of Civil Engineering Section Committee of Institution of Engineers Sri Lanka. So I think some of our most of our viewers, engineers, colleagues do know about this project. So this was the project management of this expressway done by the Road Development Authority, and MG Consultant was the leading consultant in association with so many other local consultants such as RDC, CA, Oceana, CECB, and Greentech, and IESL. And the design and construction of this Pothuara interchange was done by Maga Engineers itself. And so these are the main three parties for this project. Earlier, this project, this system interchange was belonged to section 3, but during the construction, it was transferred to the section 2, that's mean Meergama to Kurunegala section for the continuation purpose. So right, as a result of that, you can now travel from Meergama to Kurunegala continuously without any hindrance due to that decision. So we have to praise the project management division of the RDA for taking such a timely decisions. Again, now this is the plan view of the system interchange. As I explained earlier, now this is the way we are traveling from Colombo here, and this is towards Kurunegala. So Colombo, if you want to go to Kandy, so you have to take this ramp and go like this, this way. And this is the ramp way, which I'm going to describe in this seminar. And if you coming from the Galagedara and you want to go to Kurunegala, so this is the path you have to take, and you will meet the ramp D here, which we have already done. But unfortunately, this part is still under construction. So right now you can't go to Galagedara from this one. This part is already constructed, and this part has to be done. So this has been constructed, but cannot be operated. But all the main expressway is trafficable, so you can take your vehicle from Meergama to Kurunegala. So ramp A of the Pothuara interchange. So again, I think I have refreshing your mind. This is a interchange of a, we call it system interchange, where there is no entrance or exit point for general roads, but just this is a moving from one expressway to another expressway, so that we call it a system interchange. And this is a ramp A interchange. It does have 30, 35, 235 spans, and single 30-meter span and 20-meter span bridge. It's a combination of 20, 35, 30 span arrangements. And since this is a ramp, the width of the ramp is little less, so that only 4 beams were used to in the cross section to build this ramp. So this is the another longitudinal view of this bridge ramp, where you can see the 30-meter span, and this is a 35-meter span. There's a 35-meter span and 30-meter span and a 20-meter span. Sorry, 20-meter span. I think this has to be corrected. So why we use 235-meter 235 spans here is because of this road. We have to allow this traffic. So we have limitations. So we do have to use the greatest length to this span. Now, when bridge is curved and we use the simply supported girders, it is very easy to use smaller girders and get the curve. But when this type of constraints are geometric constraints are there, we have to adapt. This kind of longer beams. So we have managed uh, to do this bridge in a very short notice due to this arrangement. If I describe a little bit of history of this one, as I said, this was originally was to be done from the section 3 of the Central Expressway, but since we were given this task to build this system interchange in a short notice, we have to change the designs. Earlier it was like a box girder, but we were trying very hard to complete the project, but unfortunately this COVID and all the issues came, so that all the imports and all the things got struck, so that the formwork systems and all these necessary supporting equipments couldn't deliver on time, couldn't get on time to the site. So we took a drastic decisions to complete this project with the span arrangements, changing the span arrangements, and such a way arranging these beams. Now these 30, 35, 20 meter girders, we have casted thousands of girders for this project, so that our casting, there are several casting yards in the project. So casting of these girders were not an big issue for us. But there were no any box girder bridges in our rest of the section. So to do the box this section, we do have to get the new formwork systems and new launching systems and all those stuff. But we had the very little time. So what we did, we took our available resources and changed the span arrangements, and contractor and the RDA and the consultant work together tirelessly to achieve this target, and all these land acquisition issues were there. So kudos to all those who involved in these activities to facilitate this construction, because we just such a short notice we deliver this project with the available resources. So these are the span arrangements. And for the ramp D, it is also very highly skewed, but we managed to do it with 35 meter girders. And now accommodating this one, we have to appreciate the highway designers also, both the contractor, RDA, and consultant highway design engineers, allowing this kind of geometrical revisions in their designs, not compromising the standards, but allowing find the ways and means to doing this kind of adjustment to achieve the targets. So I have to thank all the engineers and decision makers who involved in this project, allowing this kind of progressive decisions without compromising the quality and the cost. Again, this is a cross section of the girder ram D ram. So what we have using here is pre-stressed concrete girders. If you see, we use pre-stressed girders, PSC girders, and in top of that there will be a slab. So for this system interchange, as I said earlier, there are 20, 30, 35 meter lengths, and we use grade 40 and 50 girders. And for the continuation, we use link slab. So there we use the minimum number of expansion joints in the bridges, so that you don't find any discomfort while you are riding. So to make sure that you get a comfort riding in the bridge, we use only 2 expansion joint at the start of the bridge and end of the bridge. Other than that, there is no uh, intermediate expansion joint in the bridge. Here is now this is a you put a link slab here. So this is a one deck. Now this is a 2 ends of the supported bridges here, girders, and this is the diaphragm wall here, and there are two girder decks here, casted. Now in between that we put another slab here. So we don't join these decks by expansion joint. Instead, we put a link slab here and make sure that there is no any expansion joint in between that discomfort the ride. Not only discomfort the ride, it will give some maintenance issues as well. So if more expansion joints mean more problems in the maintenance as well. So it's a riding comfort as well as maintaining purpose. This is another illustration of a picture, few pictures of the ramp T. And if you see now, this is the middle span. Now this is the main trace, and you will see that we have used 4 columns and four columns, and we have considered even the robustness and redundancy issues here, because we have made sure that we use smaller diameters column, because we can't take larger columns because of the restriction of the 2 sideways, and we have made sure that robustness and redundancy is taken into account when deciding the number of columns. This is another illustration of the ramp T, and right now you can travel underneath this bridge while you are traveling to Meedigaon to Kurunagala. And this is another picture of the ramp A during the construction, and you can see how skew is this piers, and these are the diaphragms. So again, now I will talk about the deck systems. Deck system what we have used. So this is the girder we are using. This is the naked girder. So after launching this girder, after launching these 4 girders into the substructure, there's an intermediate slab, 200 millimeter slab connecting these 2 flanges. So this is the now if we talk about the construction stages, first we launch this bridge into position, and then we cast these then we cast the diaphragm walls this in the between the girders. Then after that we complete this 200 millimeter slab. Then after, now again this is the first composite action. Then there will be another slab on top of that 100 millimeter thick slab. This is the second composite action of this girder. So there will be 2 composite actions in the different times. So during the construction, we have to take in account the effects of these things in the detailed design. Now, as I said, we adapted very low torsional stiffness deck type, minimizing the skew effects. And even we decide the number of diaphragms with a minimum effect to the which gives the minimum effect to the skew effects. So that what have we done? We have limit the transverse dispersion of the loads, and that's how we get rid of the skew effects. And good part of that one, it allows this very speed construction, and it allows us a easy launching of girders. And so those are the uh, uh, good side of that one. So what is the bad side? Bad side is design wise, this girder gets a high bending moment, high longitudinal bending moments. As a result, you have to introduce high pre-stress, and even you have to go for the uh, greater height of the girder. So anyhow, we manage such a way that we can do these girders with the available formwork. So I mean, we have casted these formworks for other elsewhere in the project. We have casted thousands of them, and we can use the same formwork system with a minor modification to cast these girders as such a way that we reduce our construction time, we reduce our construction cost, and we were able to achieve our objectives expected by our employer. So now this is a single span of a 30-meter girder. I took this picture to explain you the number of diaphragms we adapt. So there will be 2 end diaphragms in 2 corners, and there will be a mid diaphragms. So mid diaphragms were parallel to the supporting edge, so that this is also easy in the casting of the diaphragms. So our earlier we had used 5 diaphragms for our bridges. The other systems allowing more greater lateral. Since this is a skew bridge, we minimize the lateral dispersion, and we get to overcome these skew effects. So this is a longitudinal section of a 30-meter girder, and you see this is the girder, and this is the flange part, and at the corners it's to withstand the high end block forces, pre-stress forces. There's a concrete block here in the middle part, so only thin web, and this is the diaphragm section, and so this is the type of girder we have used, and these are the pre-stress tendons profiles to do the post tension. So so basically we adapt a deck and girder system efficiently to address this skewness and the curvatures. So that's a one construction and design decision we took in view of completing this project within the time and the within the cost. And when it comes to the bridge bearings, we always use the elastomeric type reinforced bearing pads. Now, what you mean by elastomeric is elastomeric reinforced is if you in there, these are steel plates are there. So in between the rubber, these steel plates are there. It will reinforce this bearing. As a result, it will take more compression and shear strain, withstand more compressive strains. And so these are the types of loading it has to resist these bearing pads. So we used this kind of bearing pads. Now with the designs, now we done several modelings of this one contractors, designers have done different models, and the consultant engineers, we did our independent models to evaluate this stuff. So we make sure that all our design calculations are similar and we get the same results, converging this stuff. So as a result, in a very short period time, we make our check and balances that we did it very hurriedly, but we make sure that all the stuff we done in a very done the things in quality assurance manner, such a way that other than the checking the designer's model, we build our own models, and we do have our own spreadsheet to check this design. So it's like an independent design checking, so that we made sure that we won't find any blunders in our design, because I have to make another point here. Unlike in we didn't have any specific period for design. The construction and the design of this project was done in simultaneously at the same time. There's no any specific phase for as called design phase. It start from the very first day. Design and the construction started at the very first day of the project. So we have to make sure that we have to allow the fast construction to complete this project within the time, so that our designs are get ready on time. So every team member in the contractor side, designers team and the consultant team work tirelessly as a team to achieve this goal. I have to thank all these members who made so many sacrifices to achieve this target. As a result, we could have completed this project within the time. So I'm very happy about that. With the later development in Sri Lanka, if we drag this project right now, I'm sure that we will not able to complete this project, and it will halt because with the problems we face now. And so I will, with this one, I will go into little detail on the modeling part. Yeah, I will go into this. I hope you can see the modeling software here. Can you see this one?
Yes.
Thank you very much. So this is the ramp A finite element model, which we have done in the IDA Civil software. So contractor designers did the same model with using CSI Bridge, another software. So consulting engineers like us, we did a separate model using IDA Civil, and we do have a global model. Global model means the global include total bridge spans and the substructure, so that we can get the global effect. And for each and every span, we do have a local model, so that we make sure that all the construction stage activities will get adequately adhered. So now this kind of models gives you the traffic loading. We can introduce the traffic loading in this bridge, and we can get all the reactive forces of this bridge for the design of substructure. So so all the loads are there. So for example, moving load, for the moving loads, we have defined traffic lanes. So these are the traffic lanes. We have introduced these traffic lanes. There are 3 traffic lanes, and there are HA and HB vehicles here. So these are the HA type. If you little bit of familiar with the highway loading, we did this design for BS 5400 Part 2 2006 version. So as per that, the HA is defined. What happens? I think I had a problem. Just give me a small second. So I showed you. I hope you can see my presentation now.
Yes, Engineer Shilan.
Okay, thank you, Mr. Engineer Prageet. So this is the RAM-D modeling, RAM-D global modeling for this one. So in this model, you can see that there is a this kind of small part here. These are we call elastic links, and this represent the bearing pads. So we have modeled these elastic links. There are 6 degrees of freedom, such a way that it has the same properties of the bridge bearing. So this is a trial and error process. We have to get the design the bearing pads based on the reactions here. So we do the bearing pads using this reaction, and then we get the results, and we get the same results inserted to this one. Again, we refine the reaction forces and see that all these bearing design and the global model reactions convergence each other, so that all are in uniform status. So we have done like that. So as I said, now what we have used the same kind of bearing pads in the project, reinforced elastomeric reinforced types of bearings. Of course, there are different sizes and different dimensions, but the concept of the bearing is same, elastomeric reinforcement. But here, as I said, there will be so many displacement deflections in the expressway in the skew bridge, so that we make a small adjustment. We introduce a small L angle to hold this bearing pads in position. Otherwise, it will with the time, with the traffic loading, and even with the temperature and the shrinkage creep movements, there will be some displacement in the bearings. To overcome that one, we hold these bearing pads tight at the bottom. But when you doing that, so part of your bearing pad is not effective. This part is not effective because it's restrained. It doesn't allow to completely. It's not involving in the movements. So we have accommodated those kind of things also in our bearing designs. Ultimately, our aim was to allow the superstructure to breathe while not displacing the bearing pads. And when it comes to expansion joint, we used expansion joint elastomeric reinforcement again. It's a combination of steel and rubber. And these are the general types of expansion joints we used. This is a cross section, and this is a typical reinforced elastomeric bearing expansion joint. We did use several sizes of bearing expansion joints, starting from 60 millimeter to 180 millimeter. But here again, as I said, due to very high level of lateral movements expected, we couldn't use this expansion joint. Instead of, we introduced modular types expansion joints, allowing the lateral and longitudinal movements of the structure. So this is the special type of expansion joint we use for these superstructures. Special types, I mean, these are very common in the world, I would say, but in this project, it was a special type because all the general types was elastomeric reinforcement type. So modular type bearings expansion joints give more freedom for movements. It's allow for the greater movements, so that we used this one, and it's a little costly as well. Let me check whether I can. So as I said, this is the global model, and so these are the available now. These are the expected deflection in the global model, but now this is a global model, so this is not the accurate deflection pattern. We have to consider part by part, considering all the shrinkage and creep effects to the picture. In this global model, it has not done. This is the basic modeling for the road traffic, and we can get the deflections of the due to road traffic and the restraint condition for this girder, this bridge, and we can get the moments and like this, and these are the moments, and we can get this stuff, different load combinations, and like that. So the time dependent forces due to creep and shrinkages cannot be evaluated from this one. For that one, we have you can see my screen. Am I Engineer Pragit? My software screen?
Yes, sir, it's visible.
Okay, thank you. So now for the construction stage, we have done a separate model for each and every span. Now, if you see, we have done construction stage. Now, this is the naked girder. We have done the casting, and we have done the pre-stressing. So due to pre-stressing, there will be deformations. Like that. So if you see, these are 50 millimeter. Due to the pre-stress, there will be a camber, upward camber, and the estimated one is 50. So now, when we are doing this one, so we have defined all the creep and shrinkage coefficients. So if we see that we have done this one for grade 40, and so this is the time dependent creep effect, and this is the graph. So we introduce this graph, and computer will automatically take all the string creep effects into this model. Or otherwise we can do it by the manual calculation also. So what we have done is there are I would say 3 kind of checking. First one is from the contractor designer itself, there is a checking. So then we do the checking their model, and we do our own model. Consultant will do all model using the softwares, and we make sure that we do have a separate spreadsheet designed for this time-based, time-dependent force evaluation. So we make sure that our spreadsheets and the software give the same result, reasonable tolerance, so that we make sure that our designs are super fast, but those are very correct as well. This kind of tedious design check and balances was very much necessary, because we were doing the construction and the design in the same period, and we have to cater the construction requirement, construction targets, without delaying the design out. So all people were in a very stressed manner, very hard working, and so this kind of check and balances were adapted to ensure that the safety and the durability of the structures. And this is the grade 40. We have to define these graphs. This is the compression with the time the concrete which achieve the strength. So if you see now, just after the casting, within the 3 or 4 days, we do the pre-stressing. Within the 7 or 10 days, we do the pre-stressing. So we have modified our construction stages such a way that we will now this is the first stage, cast and pre-stress, and after getting the strength, let's say you get the strength of your casting compressive strength, we do the pre-stressing, and then after another 2 days, another about 30 days, we do the launching, and then another 15 days we do our diaphragm casting, and then we do the 20 millimeter thick wet concrete between the flanges, and there is a wet concrete, and after getting can you please check your mics, because I'm getting some disturbances. We can mute this one now. Can we mute this one? Engineer Pragit, can we mute that mic?
We can't mute.
Dear participant, can you check your mic? We are getting some disturbances.
Yeah, Engineer Damita,
can you please check your mics? Engineer Damita, can you please check your mic? Engineer Damita, can you hear us? ini Kamita
පාඩම් කරවල ළමයාව මිරිකලා ඒක ලියවන.
these are the common problems you have to face, so you have to tolerate this one. Anyhow, I will go through this session. It's all right if others are tolerating. So then we do have the 300 millimeter wet thickness and then there will be a composite. After this wet concrete get hardened, there will be a composite action, so that
ප්‍රොෆෙසර්ස් ටික අල්ලගෙන A level වලට පේපර් එක හදනවා. ඒගොල්ලෝ හදාන්නේ පේපර් එක ඒගොල්ලන්ගේ
someone knows this engineer very much thankful if we can inform him.
පේපර් එක හදාන්න දෙන්න
Called him.
පන්න පේපර්ස් ටික.
Seems to be he's not hearing our voices. Okay, so I will anyhow I will continue with this one. So once you get the composite action, the action is there. Then there is another concreting, 100 millimeter wet concreting. It will take another step, and
Yeah, hello.
and
Excuse me. Could you please everyone mute your mics?
okay, thank you. So the last stage is about construction of barriers and put the wearing courses. So that is also done, and the final stage we do allow about another 10,000 days to with all this one to allow full creep and full shrinkage effects, so that all these construction stages are incorporated into this model. And with that one, we now after pre-stressing, this is the deflection. Now after during the deflection, let's say within another 30 days, there will be a different deflections when the which launch is there. Then with the casting of diaphragms, deflection is reduced due to this weight and load dispersion. So like that, we have to check all these deflections, and before the concreting and before do the asphalting, we do check these deflections theoretically, and at the site also we do check manually. So we make sure that all these deflections are somewhat in a same region in the theoretical as well as the calculation. So ultimately there will be no any sagging part in the sag in the deck, and if there's a sag, there will be a water stagnation in the road, and it when during the rainy it will be pooled, or there will be a small water film in the bridge. With the high speed, these small water films is very dangerous. It will skid. So we'll make sure that safety of the traveler is there, which are very hard, given a very high level of design checks during the design as well as during the construction. So when it comes to the expressway designs, this is one other aspects which we have to do with comparative to other road structures, where we have to very careful about these stagnation of water and water films in the bridge or in the even in the normal highway expressway surface, so that no accident will happen during the rain time. So these are the local models we have done, and so ultimately we do the final design, and this is the final design shape, and even we get the bending moments for this stuff, and and we can get the what is the load now. If we want what is the critical loading for this critical beam, we can check that one. Uh, So if we want to get the maximum bending moment here, this is the typical moving vehicle load loading. So this is the KEL, and this is the uniform load. So this is BS5400, and this is completely different in the Eurocode. So this has done for the BS5400 2006. So we can get what is the even HP, what's the HP type. So to get the maximum moment at this point, this is the HP loading. So many stuff can be done with this sophisticated softwares, and nevertheless, it always it's good to check with the your manual calculations or a spreadsheet as a designer. So now you can get the stresses and check all these stresses. So this kind of whatever this, you can calculate stresses at anywhere and check whether these are in line with the design specifications, and with the time these can be checked. So it's a our life has made easy by these softwares, but nevertheless software is a kind of stuff you give something, you get out of thing, you don't know what it happened inside. So that it's a very good practice to check this one doing your manual calculations. And so this is the ramp A. I will go to the ramp D also. So this is ramp D. So this is the MD global model here, and again this is we do have using for get the traffic loading and the basic reaction forces here. So to get the this kind of traffic loading we have applied, moving loads have been applied, so we can check what is the critical loading cases, and those kind of stuff we can easily do using these softwares. And after that, each span, this is a two twin 35-meter span viaduct with a skew angle of 55 degrees. And after completing this global model, we have done the separate model for the each span. So this is the separate model for the 35-meter span, the skew, and as I said, this girder has a and there is a then there will be another 200 millimeter flange section. Then finally there will be a 100 millimeter flange deck section, so that all these all these stages has been correctly accommodated into these models, so that you will get a very accurate.
Hello, excuse me, sir.
Yeah.
We can't see your screen.
Am I
Can
right?
you share your screen, please?
Sure.
I'm sorry for this.
How long I'm speaking without my screen?
I take 1 minute or something.
Okay. Thanks. Sorry. So this is the another local model we have done for 35 meter girder. And as I said earlier, there is this girder has 2 times of composite action in 2 parts. So we have to modify, we have to introduce those composite action into these girders. So first the naked girder, and there will be 200 millimeter flange, and there will be ultimately 100 millimeter thick slab. So all these has to be incorporated into the design so that it will give the results. Again, there is a construction stage for the casting, grouting, launching, and diaphragm casting, and 200 millimeter deck concreting, and this is composite action of the 200 millimeter. Then we have to do the 100 millimeter deck casting, and there will be a composite action, and after that there will be another we are allowing for the complete creep and shrinkage to be delivered. Let's say it's 10,000 days. So all this stuff is checked, and this deflections are we can get. So these are the deflections. So it will go like this one, and diaphragm casting is there. So and finally the post construction is there. We can get the bending moments, and even we can get the stresses at the each stage. So these are the stressors at the bottom, and just after the pre-stressing, and these are the top pre-stressors. So we can check all these limitations. So after, so these are the type of checks we do for the thing, and very easy to check once you model it. However, as I said, we do the manual calculation. I mean, manual calculation by our tested and verified spreadsheets, and we make sure that our modeling and the calculations are uniform and checked. So as I explained, now these are the, so we can all get the displacement and deflections for all these designs, and with that I move to another part. Now this is substructure designs for a skewed bridge. Now this part is not applicable for us in our designs, our prototype designs, because we allowed our superstructure to breathe. That means with the creep and shrinkage and all the highway loading movements, this bridge superstructure can get breathe. It can move because of the bearing stuff. But if we not providing the bearings, let's say integral bridges, all the abutment wall and the deck and cast in, monolithically, there will be no any space to breathe this superstructure. So all whatever the deformation, it will transfer to this substructure. So in that kind of structure, when you do a skew bridge analysis, you have to be very little careful. So basically, what I mean is now this is a plan view of such a skew type of structure. Now, due to the skewness, it will rotate around some point here. It will rotate. So when it's rotate, you have to be very careful in the substructure design, because there will be active soil pressure and passive soil pressure. So if it is moving this direction, this soil part is in active stage, and since there's a little more movement here, this part is passive pressure. Again, this part in active, this part in passive pressure. So just because of you adapt active pressures in your substructure, it doesn't give the correct results if this is the case. So you have to be very vigilant in your design. So different guidelines give different parameters to check this one. So I think this is extracted from the DMRB guidelines. For this is the old guideline for previous guideline for design of box structures in UK Highway Design Agency. Now these has maybe have changed for the Euro codes. With that small note, I would like to conclude my presentation. I think I was able to give you something to think in the what we have done in the Central Expressway designs and in our design practice. With that, I will hand over the mic to Engineer Prageet for your conclusion.
Thank you, Engineer Sela. We spent, I think, more than 1.5 hours to absorb the knowledge and experience about the construction technology of skew bridges in Central Expressway in section 2. Now we have allocate some 5 minutes time to ask the questions. If you have any questions, you can use the chat box, or now start the time to.
I think Engineer Prageet, there is one question. Is there further unclear areas related to Skewed which are research needed? Yes, I think so. There are so many areas, gray areas we can do research. One way is the reinforcement. As I said, I mentioned about let me check. One area is you can research about this reinforcement mesh arrangement. What is the best fit for this one, or kind of that simple kind of research. And there are some other aspects like how this will affect this specific type of bridges, like let's say with the different kind of bearings and different kind of superstructures, how will this affect? And another criteria is about bridge articulation, how it affects to the how this skewness affect to this one, and you can do some research on that one. And other stuff I can think of is like deck types. You can consider the deck types, I would say. So if you see here, we adapted deck beam arrangement. Nevertheless, there is a 300 millimeter slab ultimately to transfer these lateral loads in the structure. So now you can think about different deck arrangements, how the most economical designs, I would say, like that kind of comparative checks. You can do some research. Yeah, that kind of these kind of topics comes to my mind, but definitely there are so much other areas, some gray areas. You can do some research if you like. For robust instead of formal, it would use concrete wall. Please give your justification for this one. So what this question is about, we used 4 columns in the middle of the middle pier. So what the question is asked about the concrete wall, why you can't use the concrete wall. One thing is, this is more cost effective. The amount of concrete we have used is less than the concrete wall. And other thing is aesthetic aspect, and the theme of the theme of it's aligns our theme what we used in other part of the project, where we always use the column. So at this location only, we don't want to make change, and it gives a pleasing aesthetic aspect as well. You can see the both side of the road, and it's aesthetically pleasing, and it's more sustainable design, because we are not using we are optimizing the material usage, and that kind of arguments comes to in my mind when answering this question. And if you see, it's relative to each person, but if you can see this kind of wall construction in other expressway in Sri Lanka. If you see the outer circle highway, this kind of wall construction has been adopted, and it's individual based, but you can see when it comes to quantitative thing, mainly it's about concrete volumes, and when you do mass hundred of structures like this, there are so many cost savings from the concrete. So that was the rationale behind that one. Yeah, seems to be Engineer Jayanaka is happy about the question answer.
Engineer Asela,
yeah,
we will wrap up the session now. I would like to invite Engineer KPI Dharampala, President of Sri Lankan section of American Society of Civil Engineers, to deliver the vote of thanks. Engineer Dharampala, this is for you.
Yeah. Good evening, everybody.
Good evening, sir.
Can you hear me?
Yeah, we can hear you.
We can hear you.
Yes, President.
Yeah. Good evening to everybody. Being the president of the American Society of Civil Engineers, it gives me an great impressive to deliver this vote of thanks at the end of this session. First of all, I would like to thank our resource person, Engineer Yasela Sumanasinghe. He delivered a lecture on design and construction technologies in high skewed bridges. So I highly appreciate. He honored my request to have this lecture on behalf of American Society of Civil Engineers. He gave a very comprehensive and informative lecture covering all aspects of this topic in a highly professional manner. So Engineer Yasela, on behalf of American Society of Civil Engineers Sri Lanka section, I take this opportunity to thank you. Thank you very much. Then secondly, I would like to thank Engineer Kamala Gunawardana, always extending her fullest support on behalf of Civil Engineering Sectional Committee of the IESL. This is not the first time. Earlier also she has helped us in so many ways. So Engineer Kamala, thank you very much.
Welcome.
Then all participants, there were about more than 100 participants. It shows their interest on this kind of webinars. Finally, I would like to thank our Secretary, American Society of Civil Engineers, Sri Lanka Group, Engineer Pragit Vijaysekara, for doing all hard work in coordinating this work to make this a reality. Also, I apologize from Engineer Sumanasinghe, the inconvenience caused to you in delivering your lecture due to this disturbances caused in mid part of the lecture. So before winding up, I would like to inform the participants, we will meet you again on a similar lecture organized by Sri Lanka Association of Institute of Civil Engineers, London. That is to be conducted by Engineer Chandradasa, a very senior engineer. He worked as a resident engineer in that project. That is the first arch bridge constructed at Polpitia Arch Bridge. This will be conducted on 28 September, 5 p.m. at the Vimala Surendra Auditorium. He wanted to have this physically, so I invite all of you to participate for that also. It is going to be very interesting one. The first arch bridge of constructed arch bridge in Sri Lanka, Polpitia Arch Bridge. So with that, I won't take your time after hard work, days hard work. Now you are tired, I know. So thank you very much for all participants and safe stay. Good night.
Thank you very much, Mr. Engineer Dharmapala, KPIU Dharmapala sir, giving me this opportunity to present ourselves and our what we have done in our past in this kind of large forum. Thank you very much for your invitation on behalf of American Civil Engineer Society Sri Lankan sector and Civil Engineer Sectional Committee of Institution of Sri Lanka, Mr. Engineer Mrs. Kamala Gunawardena, and very dynamic Secretary of Engineer Pragit, giving me this opportunity to present myself. Thank you very much. Really appreciate. Thank you and have a pleasant good night.
Thank you, everybody. Good night.
Thank you, everybody. Good night.